So hi everybody, my name is Artem. I'm a data scientist, and today I would like to talk about ship from store, sourcing problems, and um, how some old framework can help us to solve such kind of problems. And uh, if you have any questions during the talk, please write them down into the chat, and we'll have some time to answer them after the talk. Okay, then let's start. So today I would like to talk about this particular sourcing problem. So imagine a situation that you have typical e-commerce business, and you have several distribution centers and stores, and thousands or even millions of SKUs inside your stores which you can ship to your customers. And you have like 1, 2, 5, or 10, or even more thousands of orders per day. Typical e-commerce situation, and you have in this situation you have a question from which orders you would like to ship your orders. So how to choose a sourcing for your orders from your customers, and because depending on how do you choose this, how do you choose your sourcing, it will define how many money you will spend on delivery. So it might be not so wise to ship to New York from California, for example. Okay, then. So this problem is pretty widely known through the academy itself, also, and also among the business itself. Here, you can see I just collected like a few links from the first page of Google search about articles about this topic. If you'd like to, you can revisit them after the talk, or just to see what people do on this matter, or just to know that Academy itself also paying attention to this problem. There are a lot of articles on this matter. And today we'll talk about some academical approach, which is widely used inside the business itself. It's called mixed integer linear programming, so or MILP for short. So essentially, those MILPs can appear from operations research. It's a mathematical field appeared after the World War II. And right now it's used for optimizing a lot of business supply chains, manufacturing, and all other stuff. Most of the problems inside this operations research are combinatorial optimization problems. So that means that you have some matters that are integer in their nature. For example, item. You can ship half of the item from one store and another half from another store. You have to ship the item as a whole. And this poses a lot of computational difficulties for, for optimization. So essentially, MILPs consist from three main objects. It's variables, constraints, and objective function. Variables is describe your decisions. So in the variables, you write down for example, from which store you would like to ship this particular order or that particular order, or maybe you would like to ship an order from 2 stores, and how many items you would like to ship from store A, and how many items you would like to ship from store B, and etc., etc., etc. Anything that you would like to make decision on, you should write inside your variables. So then there goes constraints. So you can't just assign some arbitrary values to your variables. You should follow some business constraints that you have. For example, you can't ship from any store, you can ship more than inventory available in the store, for example. And also an objective function. So there are a lot of possible shippings for for ship from store, a lot of possible sourcing for ship from store. And and you would like to choose the one which brings you the most value. For in our case, the one which costs you the less and saves you a lot of money. So also, as I said, in MILPs you have some of the variables can be integer. So just not to make a decision about, like, for example, cutting your item in half and ship one half to one man and another half to another man. Meanwhile, still you can introduce into this framework some continuous variables if you'd like to. Also, there is a word linear inside the MILP, and linear stands for that variables that constraints and objective function you would like to have should be linear. Just a second. Should be linear. Linear means that you can sum up two different variables or multiply them by some known fixed value, but you can't multiply variables between themselves, or take a maximum or minimum between them, or make an if condition on them. Well, because that's non-linear operations, but they can be proxied inside this framework. If you give up on the integrality of your variables, you'll get perhaps some of you know a framework that's called just linear programming, and such problems can be solved pretty easily with, for example, simplex method. So let's go ahead and compare those two frameworks. So in this picture, you can see, for example, you can see a red area, which means all the possible continuous solution for your problem. Well, in our case, it's a ship from store, a sourcing problem. And the blue dots inside this area is an integer solution. So the solution that we are interested in. And the red star here on the right is the best continuous solution. So if you can, as you can see, continuous solution is it's different from the integer one, and it's not easy to determine which which integer solution is best in this situation. So this is a known problem inside academy, and well, as I will talk later, nobody knows how to effectively cope with that. So okay, let's try to make a mixed integer linear program on our problem. We'll have to introduce some definitions. We'll have three sets here. The first one is a set of orders that we would like to source from our stores ODCs. Set J is our possible solutions, and set K our possible sources, and set K is all different SKUs inside our business. If you see throughout the presentations any subscripts with I, J, or K, that means that those values are indexed based on those sets. So for here, DIK means how many items of type I you have inside your how many items of type K you have inside your order under number I. SJK is the amount of inventory for for item K in store J, and CIJ is how much you should pay to ship anything on order for order I from store J. So there we have three. Those are the parameters of our problem. So we every day we have we have a new set of Ds, and sometimes maybe and send updates on our supply, on our inventory, and also some shipment costs can change from day to day. Now we have to construct the MILP. We have to determine the variables that we have. In our case, variables are we have two set of variables. The first one is xijk, which means how many items of type K we would like to ship from store J for order I. For example, if somebody ordered an item 1 from we should assign at least for at least one of these variables, we should assign some value, and subscripts in this variable will denote from which store we would like to ship this ordered item. Another set of variables is dependent from the first one. You'll see why we'll need it further inside the presentation. It's a binary variable. It will equal to 1 if store J is used to fulfill the order I. So we have variables. Now we have to set a constraint for our problem, and the first constraint is that we would like to fulfill the order itself. So if we take all the shipments from each store that we have here, that's why we have a sum here from store 1 and store 2 and store 3 and so on, and sum them up, we should get the value that is equal to amount of items which was ordered by our customer. The second constraint is that we actually can't ship more than there is an available inventory in the store. So that's why we take the sum over all the items, all the orders that we have for the store for this item, and see if we are not trying to overship items. That's our second constraint. The third constraint that we would like to have will establish the connection between X and U's variables. And if you remember the definition of U, it should be equal to 1 if any of the X's is greater than 0. So if anything is shipped from store J for order I, then this variable Uij should be equal to 1. That's a typical if condition. So if you write in a Python program, you just wrote if any of X's is greater than 0, then Uij equal to 1. But Meetup can't handle if conditions. That's why we are using this modeling technique. We multiply U by some big constant T and compare it with the sum of X's. So this sum can have different values, but they are all limited. So we know how much items we would like to ship today. For example, if you have 10,000 orders and inside each order we have like 5 items, then we should ship at most 5,000 items. And we could set T here to equals to 5,000. It's an artificial one, of course, but it works. So, and the last thing that we should have inside our Meetup is our target function. So target function here in our particular case stands for how many money we will spend on this particular shipment, and that's why we multiply all the U's by the shipment costs for this store to this order, and take it all together. And our goal is to find the cheapest one, the cheapest assignment, the cheapest sourcing that we can get. Just a second. So if we put it all together, then we will see this picture. If any of you will be interested in scientific articles, you'll see such kind of pictures all over the place. So essentially, it means that we would like to minimize this target function with the subject to this set of constraints. So the target function we just discussed. The first constraint is that we would like to fulfill the order actually. The second constraint is about not exceeding the available inventory in each store. And the third constraint establishes a link between variable X and variable U. So as you can see, as you can see, we were able to describe all the problem in terms of mixed integer linear program. But those models are Turing complete, and you can actually add here some other stuff that your business requires. So, for example, if you want to use no more than some fixed amount of stores for each of the delivery, you can add a constraint from the first bullet of this list. So total amount of used stores should be no greater than some given value. Or, for example, you also pay some price for shipping some particular item. So some, for example, if you if you ship in refrigerators, then you have to kind of pay a little more money to your haulers because, well, they don't want to ship refrigerators for free. They would like some money for it. And that's why you can also add some item dependent cost into your target function, and and this issue will be also considered inside your model. Even more than that, in the academy recently, models also contains even carbon dioxide emissions. So you can actually add such kind of emissions into your model just as in the same manner as shipping cost. For example, if you use some of the haulers and they emit a lot of CO2 into the atmosphere, you can also add it to your model and modify the target function to take it into account. So the model would like to discriminate the solutions which make a lot of carbon dioxide emissions. So okay, let's go ahead. Why the bad news is for this sourcing problem is that this sourcing problem is NP hard. NP hard problems is problems right now. It's a problems that humanity don't know how to solve effectively. Essentially, there is no other approach from the brute force that can be used to solve such problems optimally. It's one of the millennium problems. If you find one way to solve such problems in a fast way, other than the check all solutions, then you'll get $1 million from Fields Institution. The problem, why it's so hard to solve, is because the amount of such solutions grows exponentially. If we open one another store or add one SKU to our shipments, amount of possible solutions will increase roughly 10 times. And already for such kind of toy problems, for example, if you have 10 stores, just 2 SKUs and 11 orders per day, you already have like 100 billion solutions. And just to brute force all of them, you'll have several hours even on your laptop. But if you try to brute force the production scale sourcing problem, then it will take like trillions of years, even with the greatest computers that humanity have. And another bad news is that a lot of real life problems that the industry faces right now are NP hard. I guess I hope I think some of you already faced such kind of problems. If they worked with supply chains or logistics, then you can maybe face you might face a traveling salesman problem, or even if some of you worked with the compilers or hardware loading, you might face a bin packing problem, or somebody maybe who is heavily into the clusterization also knows that even Kamin's problem is even Kamin's approach is an NP hard one, and Kamin's algorithm it doesn't yield the best possible solution. It yields some perhaps good solution. So why do we need those MILPs in the first place? Those MILPs are required to actually those frameworks allows us to solve such kind of problems, and we have two different possible approaches to solve them. The first one is to use heuristics. So if we give up on obtaining the best possible solution, we can try to focus on getting just a good solution. In this case, we won't have any guarantees on the solution quality, and it will be even hard to estimate how good our solution is. So we won't be able to say that our solution is like 10% away from the optimum, or 20% away from the optimum. We just won't know that. In order to estimate that, we will have to spend a lot of resources. And another one is branching cut approaches. Such approaches stands that instead of checking like each and every solution that we have here, we will check just every subset of such solution. For example, we will compare a subset of solutions which ships from California to New York, and such solutions will cost much more than shipping through New York from New York. That's why we can just discard all the solutions which are bad one and continue with a good one, which are inside New York. So this approach is handled by adding additional constraints, like setting one particular variable to one particular value. As you can see here, we are branching on the variable u and setting one of the variables equals to 1 and another one equals to 0. So the pros and cons here is that we are getting optimal solution and we are getting it with a proof, but there are cases for each of the problem. We can find a case when our branch and cut method will be as bad as as a brute force, and also such kind of approaches are not so scalable. Their execution time grows very fast, much faster than for heuristics, and that's why it's hard to scale them to the bigger one. Today we will focus on the second approach, on the branching cut, but just be aware that heuristic can also be used to solve such kind of problems. So why the MILPs? As we discussed later, MILP can be converged just to linear programming that can be solved efficiently with the simplex method by giving up on the integrality demand. So that will yield us a lower bound, and lower bound means that best solution in this particular set is no better than this value. So we take our MILP, we remove the constraint on some variables to be integer and allow them to be continuous one. Then we apply a simplex method for them and get some value, and this from the simplex method, and this value will be our lower bound, which we can compare with some upper bounds in other subsets. And upper bounds effectively stands that best solution in this particular subset is no worse than this value. Upper bounds can be obtained from, for example, just some solution, not the best one, but maybe some good solution. And then during the work, we always compare lower and upper bounds between our binary search tree. It's effectively a binary search, actually. And if we see that somewhere lower bound is bigger than upper bound somewhere else, then we don't need to explore this branch further, because we already know that somewhere else there exists a solution which is actually better than any solution in this particular branch. That's why we discard it and continue to work further. So I described this in a very brief and questionable way, just because we actually don't have to implement this by ourselves. There exist some solvers, packages of software which can take your problem described as a mixed integer linear program and find you a solution, and you don't have to code any of this. So they just take the MILPs and give you the answer. The problem is that, as I said, most of such problems are hard to scale. So even the best solvers won't be able to handle huge problems. There exist a lot of solvers, a lot of different solvers on the market, both free and commercial. So I listed just 3 of them in each of the categories. So the second one from 3, OpenMDAO, it's made by NASA institution, for example. Octaplanner is open source optimization software for Java. If you'd like to. From commercial one, the best one is Gurobi. We will compare today. We will compare the Gurobi here with the Coin OR CBC solver. Also, there exists IBM Cplex and Knitro. Just you to hear the names that such stuff exists. And as we will see on the next slide, commercial software usually heavily outperforms the free one. And you can see here that we take a CBC solver and the Gurobi solver just for the sake of demonstration, and two sets of test examples. They are different. The second set is just twice as big as the first ones. So in first one we have 20 orders, 5 SKUs, and 10 stores. In the second one we have 40, 10, and 20 correspondingly. In each set we'll have 20 random examples, just to make it faster a little bit, because it's a hard problem, and it will take some time to calculate even for one of them. And also you will notice in this table that somewhere we have like dashes or signs like greater than. It means that actually a CBC solver wasn't able to cope any case within 5 minutes for the bigger set. So as you can see here, for smaller sets, their CBC and Gurobi works like in the same very comparable between themselves, with Gurobi being a little bit better than CBC. But for larger sets, CBC just failed to work, while Gurobi works like within 1 minute for most of the cases. So that's it. Now you know that such problem exists, and that you can try to solve them with the solvers. Also know a few solvers by yourself, and can go on with and you can try to work on it. Then let's see. Looks like we don't have any questions inside. Don't have any questions inside inside our chat. So if anyone have any questions, you can write them down right now, or we can go to the next speaker. Yeah, Ivan asked where I get in touch with such methods. So essentially, it's my PhD thesis from university. You can also find my works on the Google Scholar, where I was handled with mostly bin packing problems with some additional constraints. So it's academic. So I know about them from academy actually, and asking. Well, I was studying in the Novosibirsk State University. Well, it's Russia, obviously. but I also worked on University of Pompey Fabra in Barcelona with the same actually with the same thematics. They also have operations research lab there, and such kind of labs are, well, they exist like everywhere. It's it's a widely known topic within within the management science. Also, like answering on some maybe other questions that you'll have. The problem that I showed today is actually was on one of our accounts. I just won't say which one, and it actually yielded us. It actually yielded a two-digit increase in earnings before interest and taxes. So it's I'm not talking bullshit here. It actually works. Okay, then if we don't have any other questions, then I think we can go to Ivan. Ivan, can you hear me?
Yeah, thank you.
Yeah,
for the presentation. Hello, everyone. I'm Ivan. My name is Ivan, and 1 second. Can you see my screen?
Yes, I can.
Okay. And today I want to tell you how business can transform their processes with using machine learning algorithms for managing some risks in an environment where a company has to think about logistic and delivery processes. I will show this on the example on one of project when we finished some time ago. This is my plan. Firstly, we have a little talk about goals of the project and some objects and things that you have to know about it. Then we will speak about how project was going, and after that we will discuss results of this project and potential next steps of such solution. Sorry. Okay. So the project was about some business, what was about subscriptions. And from this point, when business grows, it has several problems from the point of logistic and delivery. And we decided to create some proof of concept, the first solution that can help to solve such problems. And now on this slide, you can see a simple scheme of what is going on. So every customer has his subscription. Also, every client can have several subscriptions, and every of them has one of the three statuses: post, active, or cancelled. And on the slide, you also can see an example of customer path. So every week he has some status for his subscription. Active gives us understanding that he get his delivery. Post get us information that he don't want to get his delivery this week, and he can cancel his subscription to not give any goods from the company and not paid for that. And from this perspective, we have three big problem types. It's pausing. So when client pauses, company has to think and plan these values that they have on their warehouses and amount of people who involved in delivery process. Second type of problem is cancellation problem. So simply after client don't want to pay buy company products. It's a not good way of developing. And third problem is quite different from the first and second, and it's about reactivation. So when client, when some person was client of company, then his subscription was cancelled, and company changed product or maybe sent him a relevant offer, and he decided to return to using company product and pay for them. On this slide, you can see an example of how such prediction can be used. Client want to have prediction for several weeks in advance. So here you can see 4 next weeks, but number of weeks depends on use cases where prediction will be used, because in different of them, you have different forecasting horizons, and you can do different actions. So for example, it can depends on from what time you can cancel delivery to you on some products that you after want to deliver to your customers. And moreover, such prediction can be used as basis for some recommendation system that business can create. So as you can see also on the slide, this is example of actions, and for some customers, we can send offer about and pause. For some, we can sell some additional subscription, reward loyal customers, and try to reactivate customers who was exit. A couple of words about what we did specific in our project. It was about 4 months long, and we started with exploring data sources that company have that can give us understandings of what we can use. After that, we go to the exploring data and try to get some insights from this data and correlations with target values. And for us, target values was explicitly status of customer for next week. And after that, we created first version of model. Then we added additional sources to our data and created some new features. After that, we created pipelines for automation of this process. And in the end, we create final pipelines with training model and scoring model. And also before that, we tune params to extract the best results that we can from this data and from this model. To speak about technical points, we developed on Databricks, and as data source, we use Spark. And our final version of a model was CatBoost, but if we speak general, it depends on which algorithm was the best, and you always have to do some comparison between different of them on different feature samples to have the best one. To speak about data sources, we had several data sources, but their nature, but their source. So as example, we have customer data, something about age, emails, where are they from. We have also additional geography data about warehouses, distance to customers, delivery points, and so on. Also, we have calendar data, because holidays are important point when we try to plan some deliveries, not only from the point of works day or not, but also from point that holidays sometimes has a trend when customers buy more. And our big source of data was about orders, about deliveries, and about product parameters. And this three big data source give us some embedding for different types of clients of his actions with their subscription. Also, we have CRM data about which promotion was sent in what channels to the clients, and clickstream data about how customers interact with app and website of the company. So as we have multi-class classification task, we had two options. First, our options was to build model for every week. So one model for first week, one model for second week, and so on. Or create one model and add as features some label which we want to predict. The simplest approach to do this is create specific label, for example, one when we want to predict first week, two when we predict second, and so on. But we went further, and we want to create features that was not only a label for week, but also can give us some additional information about distance inside week. So we create features that show us days between prediction day and delivery day, and it combines for us understandings which week we want to predict, and also how long time before delivery day we have inside week. And also, when you create a model for business, you can't use the same metric that are using for optimization. Sometimes it can work so, but in most cases that I saw, it isn't. And on this slide, I want to show you examples of how we measured the result of this model for the business. This is two examples. We have some more additional, but this two was the main. So first, what business want to see is that how many customers we correctly identified as post. And for this, we choose recall and past clients, because recall is a ratio between true positive and sum of true positive and false positive. So in this metric, we try to minimize amount of customers who was not post and was predicted as post. It needed in this case because if client was active and he was predicted as post, but he hasn't changed their status, and we will send them some promotion based on our prediction. About unpausing, it can give us negative feedback, which can lead to some problems that business don't want to face. And second one metric that we use was quite easier, is about error on aggregated values of how many active customers we predicted right. This value can be used in marketing and planning purpose. So they also want to see how it goes on. Okay. And here you can see how we created new feature based on sources that we have. On the slide, you can see that features in the right side of slide has two sources, but in fact they have 3 dimensions because we don't only use these 2 sources. One of them is pause actions, and it includes pause and unpause actions for every client and time for that. And second source has a status for every week from the client registration. As we have 3 dimensions, we have pause actions, week statuses, and timeline of these actions. We created historical features of how many actions of which type was on some historical interval. As example, there is 3 weeks and 6 weeks for 2 types of actions, but we created a lot more, and after feature selections, we left only that he give us most impact in the result. And here you can see another example of new feature. And this feature give us, as you can remember, not cancelled user can pause and unpause their subscriptions. And we decided to calculate distance between delivery day and have a look on number of clients with similar values. And on this picture, you can see 2 trends. First one is for pausing clients, and trend that amount of clients who has pause actions with particular days before delivery day increase with decreasing distance to delivery day. Increase with distance to delivery day. And for unpaused actions, we have different picture, or opposite. The maximal value of unpausing actions is quite near day after which customer can change anything about their subscription. And this gives us understanding that such model can be useful in the point of predict such pausing clients and to plan them better. After we created most of that we did, our data pipelines, our models, we go to some automation about it to give client ability to use these results of these projects without additional development. So we combined all what we have in pipelines for terrain model and score model. So we have daily jobs for collecting new data and to calculate different features that we created. And then we create pipeline for scoring and training model. All this process was logged with MLflow, so model can be versioned, and for every experiment you can get access by ID. To speak about results, we compare our result with current approach this company had, Current approach is based on live status for client. For example, if client is active and he haven't any post and cancel events for several weeks ago, he will be active. And such approach has a benefit that he can predict active clients quite good because he can't it approach can't catch some posing actions that will be after days that we calculated this live status. But as you can see from this slide on paused clients, we have a much greater result. Comparison metrics is a MEPE, this is a mean average percentage error. And also you can see that error of is increased with when horizon of prediction increased. And after that, we can do some additional actions to upgrade such approach. So our model was more related to predict pause clients right, also because client pausing has some actions inside it, and some of active clients don't do anything with their subscription until they canceled it. What a company can do after such research? They can continue current project. So we suggest to divide this model on 3 for every problem type, because if pausing and cancellation has the similar nature, so reactivation is mostly based on emails, and it can be confusing from the information about current clients that we have in our data set. Second is that company can create a recommendation system that will be use such prediction as information for making decision. And third, what we suggest is a long experiment for widening weak point of the model in live mode, and maybe create new features to resolve them. Other ideas that we have during our project, and that we also can suggest to solve some such business problem. First is the simplest is market analytics. I want to mention that as beginning of project, we have and conditions that we don't use external data because it can take a lot of time. Another idea that we have during this project is use neural networks approach for predicting statuses. It can be a deep neural network with flat vectors and features and different architectures, and maybe it can catch some correlations that our model don't. Or CNN architectures that can use as features and metrics where row will be embedding for some week and every row will be time related. And also a good point to try sequence predictions, for example, such as RNN or something other to predict customer status, because as you can see from the beginning of presentation, statuses of customers is a sequences. So our approach that we use in this proof of concept can lose some information about order of these statuses. And we decided to use this approach in 2 big use cases. First is targeting promotion campaigns in different channels, and second is use these predictions to planning workload and warehouses and delivery. Thank you for your time. I can answer your questions now. I will check the chat. Okay. Because question is why interval was chosen 3 weeks interval instead of 1 week. If on your previous slide it seemed you try to teach ML with 1 week models. Okay, we try to create some historical information about statuses and behavior for some period, so model can catch can catch this information and give us a better prediction of what will be in the next time. So on the slide, it's only in examples. We not use only average values. We also have a maximal, minimal, and other statistical functions of on our aggregated values, but this horizons in the past was using as not embedding but some representation of which behavior customer had in the past. If anyone has any additional questions, I can answer that. If not, so thank you for your time.
Thank you, Ivan. Bye.